This is Audiovisual Lecture 9, Part 2. So we're talking about short field and takeoff and landing distance and the difference between the 50-foot obstacle versus the ground roll. So two numbers that we're going to also look at are Vy and Vx. Now these are, as you know, the V, or for velocity, are the speeds that you do certain things within the airplane, and you have a V uppercase and then a lowercase letter or a couple letters next to it that show what it's for. VR, for instance, is your rotation speed. FE, for instance, would be your maximum flaps extended speed, and so forth. And so we have Vx and Vy are two very important climb speeds. Vx is your best angle to climb, and Vy is your best rate of climb. Now Vy is an efficiency number, and that's going to give you the best altitude over a certain period of time. So when you climb in feet per minute, for instance, that's giving you a rate of climb over time. That gives you, in a measure of time, you'll climb a certain distance, and this factors into your cruise performance and so forth. Your best angle, on the other hand, or Vx, is giving you the best angle of climb, so it's the best amount of altitude given a certain distance. This is useful in a takeoff scenario when you're trying to clear these trees down here. So Vx is giving you the most amount of altitude upwards that you can get in the distance from here to here, which is what you want. In that maximum climb scenario, you really don't care about how fast you get anywhere or how much altitude you get over a given period of time. All you really want to do is get as much altitude as you can in the distance that you have so that you clear the trees at the end of the runway. So that's Vy and Vx. Vy is your best rate of climb, Vx is your best angle of climb. And when you look at the technique for short field takeoff, short field and soft field takeoffs, you'll see those numbers factoring into it quite a bit. All right, so let's just take a look real quick at some of the takeoff performance. The operating handbook that we're using gives you 3 different weights to use: 2400, 2200, and 2000. Those different scenarios. We'll look at the one with 2 weights on it just so you can kind of see what we're talking about here. So there are several variables on these charts that we're using. So you've got your the total weight of the airplane. That gives you a rotation speed, and it's going to be the same for all these altitudes. And it goes by weight. At this weight, this is your liftoff speed here. So 49 knots is your rotation speed, or that VR, and the speed that you're shooting for at 50 feet is that 54 knots. You also have a pressure altitude, because remember, as you go up in altitude, the air gets thinner and your performance generally decreases. So you'll notice that all these distance numbers increase as you go up in altitude, because it's going to take longer for the airplane to get up to that takeoff speed because the air is thinner. So you're not putting as much air over the wing. You're not putting as much air through the engine. The mixture ratio is not as full as it might be because there's less total air. And then you also have a temperature component as well. And you'll notice as the temperature goes up, so sea level, your ground roll is 650, sea level at 0 degrees Celsius, right at freezing, versus 40 degrees Celsius at sea level, which is pretty hot. That's about 110 degrees Fahrenheit. Gives you 865. So that's just over 200 feet of distance just at sea level. Now you look at at 8,000 feet, so somewhere around Yellowstone or something, you've got 1,410 at freezing versus 1,925 at over 100 degrees Celsius, and everywhere in between. Now this is just for the 2200 weight bracket. If we look at the 2400 weight bracket, those numbers change again, because heavier weight, you've got less performance. And once you get to gross weight, which is this 2400, if you come all the way over here to 40 degrees, at 8,000 feet of altitude, you'll notice that there's no calculated number. And this is because this is just, it's outside the performance envelope of the airplane. It doesn't mean that it won't do it, but it just means that the airplane has either only been tested to this point, or the people who built the airplane are really only willing to say for sure that it should do this, that, or the other at this condition. And at that much altitude, at that high a temperature, with this particular airplane, they're pretty much telling you this is really not a good idea. This is not what the airplane was designed to do. You need a bigger engine, or you need less payload, or you need a cooler day, or something needs to change, but those conditions just aren't really a good idea. These charts, like I said, are fairly easy to use because all you need to do is find the information, the parameters on the chart, and it will give you a number. There's no actual calculation involved. Now, the other thing that we also have that we should look at and definitely pay attention to are the notes that are going to be given on here. You have certain conditions. So up here, for instance, you have flaps at 10 degrees, full throttle prior to brake release, paved, level, dry runway. So if you're on a wet runway, or you're on an upsloping runway, or you're on a grass runway, these numbers suddenly aren't applicable. And this also means that zero wind, right? Because a headwind is going to shorten your takeoff distance. A tailwind is going to greatly increase the distance. In the notes, we've got short field technique as specified in section 4, which is just telling you here is the way to take off in this airplane that's going to give you the shortest distance. Taking off from fields above 3,000 feet in elevation, the mixture should be leaned to give maximum RPM and full throttle. So as we were talking about in the systems lecture about getting the perfect stoichiometric ratio, this is assuming that above 3,000 feet of elevation, so somewhere out at the base of the Rockies maybe, you're adjusting the mixture on the ground before you even take off for that. We can decrease these distances 10% for each 9 knots of headwind. So sea level at gross rate at freezing, we've got 795. So if we have 9 knots of headwind, we can take 10% off of this number because that headwind is going to get us off the ground faster. With tailwinds up to 10 knots, we have to increase the distance by 10% for each 2 knots. So if we have a 2-knot tailwind, just 2 knots of wind, that's actually less than calm as a weather reporting device is going to show. We've got to add almost 80 feet to this number. So tailwinds are really not a good idea. And for operation on a dry grass runway, we can increase the distance by 15% of just the ground roll number. Just the ground roll number, because once we get off the ground, it doesn't matter if it's a paved runway or a grass runway, we're still going to need the same distance to clear the 50-foot obstacle. So those notes are extremely important to consider, especially just in the case of the winds. Now, a note of caution about winds. So the headwinds, as we saw, we can use to decrease the distance that we need to get off the ground or to clear the 50-foot obstacle, right? So you're doing your performance calculations in question 3 from the quiz, and you've noticed that you forgot to factor in the headwind, and all of a sudden it works. You put in the headwind, you can decrease your distance by 10% because you've got, let's say a 9-knot headwind. But do you really have the 9-knot headwind? And if that's what you're counting on to get you over the trees at the end of the runway, even if the ATIS or the weather reporting at the field is saying there's a 9-knot headwind, there's really no way to know for sure. You can feel the wind, but how hard is it blowing? And even if it is blowing at 9 or 10 knots, how do you know that when you take off, at the moment that you pull back on the stick, there's still going to be 9 or 10 knots of headwind there? And if there's not, you might go into the trees, right? So you never want to cut it that close. That just gives you an extra safety margin. Here again, the book says that you can do it, but you have to play everything on the safe side of caution. So definitely factor all of those notes into the final number that you have, but don't rely on it. In other words, if one of them goes away, the wind can stop blowing momentarily, very easily. So you don't want that to be the only thing that's going to get you over the trees. Cruise performance is going to be much the same as far as considering altitudes. The one thing that this is giving you, it's only giving you 3 possible temperatures. Standard temperature is 59 degrees Fahrenheit or 15 degrees Celsius, 20 degrees Celsius above, and 20 degrees Celsius below. So at your cruising altitude, let's say you want to cruise at 6,000 feet, you can set the RPM, with the throttle to these different numbers here, all the way from 2100 RPM, a fairly low cruise setting, to 2600, which is going to be a pretty high cruise setting. And those are giving you the power numbers. So this is the percent of power that the engine is capable of producing, the knots and true airspeed, and your gallons per hour. So this is how, on a performance problem, we would be calculating how many gallons per hour we're going to be burning. And that's relevant to the weight and balance, right? Because if you fly for 2 hours burning 10 gallons per hour, you know that you're going to burn 20 gallons of gas total, and you know that gas weighs 6 pounds per gallon and for aviation fuel. So you know that you will have burned 120 pounds of fuel, so you're going to be 120 pounds lighter when you land than when you took off. That's also going to affect your CG, right? Because as you lose that weight, your CG is actually changing in flight. So all those things are things you have to consider. So just as an example, let's say that we're going to cruise at 6,000 feet of altitude. We're going to set our power at 2400 RPM. It's right at 59 degrees Fahrenheit. Let's say it's a nice 60-degree spring day. So we're at 2400 RPM under the standard temperature column here, because we know that's right at about 60 degrees Fahrenheit. So 2400 RPM gives us 63% of our available power. Our speed is going to be 107, and we're burning exactly 7 gallons per hour. There we go. So that would be an example of that. Now let's say we want to go at 4,000 feet. So we just drop down a column, find our 2400 RPM, come over to the standard temperature column, and we're going to say, so that's 59% power, 65% power, 108, and 7.3 gallons per hour. So we're burning just slightly more fuel, we're going 1 knot faster, and we're making a little bit more power. So that's how we're doing it. Now, realistically, let's say the temperature is 80 degrees Fahrenheit. That's not quite 20 degrees Celsius above, and it's not quite standard temperature. So you've kind of got to interpolate a little bit to get the exact answer. So for instance, 20 degrees above standard, that's 35 degrees Celsius, which is approximately 100 degrees Fahrenheit. So 60 degrees, let's say, is standard. 100 degrees is 20 degrees Celsius above it. So let's say it's 80 degrees. It's right in the middle. That's kind of an easy thing to do. All we're going to do, we're going to calculate for standard. We're going to calculate for 20 degrees Celsius above, and then we're going to split the difference. So at 4,000 feet at 2400 RPM, we're burning 7.3 gallons per hour at standard temperature and 7 gallons per hour at 20 degrees Celsius above standard temperature. So theoretically, at 80 degrees, which is right in between the middle of them, we're burning 7.15 gallons per hour. Does that make a difference realistically? Not really. But that's the way that you would calculate when it doesn't fit precisely into one of those categories. And there's only 3 categories really, because the numbers are going to be really close to it in most instances. That's also the same way that you would calculate the takeoff and the landing distance when the numbers are, let's say it's 5 degrees Celsius, but the chart only has a column for 0 degrees Celsius or 10 degrees Celsius. You would just calculate both the 0 degrees and the 10 degrees and split the difference between it to interpolate down to the right number.